rates and working out orders. This video is going to go through from page 18 on your notes, questions 4, 5 and 6. It's just a recap of how we're working out orders, and also then how we're working out, once we know the order of each different component, a new rate given a different concentration. So here you go. Here I've started off, and apologies that this hasn't come out. We've got an experiment column here, so we can just identify each of these different experiments. So to start off with, let's look at NO2 minus. We'd want to work out what order the reaction is with respect to NO2 minus. We're going to use experiments 1 and 2 because here NO2 has gone up and NH4 plus has remained the same. So we know that the rate can only be affected by this change because there was no change there. So here I can see if I divide 0.02 by 0.01, I'm going to get 2. Don't trust me? Check it on your calculator now if you're not sure. So I'm going to say then, to get from 0.01 to 0.02, I am going to times by 2. Lovely. Now, look at my rate. Don't take my word for it. 10.8 divided by 5.4. That also should give you 2, meaning that 5.4 times 2 gives you 10.8. So here, again, we've got an increase of times 2. The rate has doubled. As the concentration doubles, the rate doubles. Therefore, with respect to NO2 minus, you have a first order reaction. Now considering NH4 plus, looking again at the different experiments, here we can see experiment 3 and 4, NO2 minus has remained the same concentration, so we know that any effect on the rate then is only affected by 0.02, here changing to 0.04. Again, if you need to work out the scale factor or the increase here, we can do 0.04 divided by 0.02, and that, don't trust me, do it. That goes, if you times 0.02 by 2, you get 0.04. So we've got an increase by times 2 here. Again, working out the increase here, 21.6 divided by 10.8 should give you 2. So we've got an increase again of times 2. So once again, this time with respect to NH4 plus, we have a first order reaction, or rather I should say NH4 plus is the reaction is first order with respect to NH4 plus. Sorry. Now I will scroll down and give you a model answer, but what I want to do at this point is, while we keep the table in view, I want to just look at the hard part of this question now. Once you've determined what the orders are, both being first order, then the question asks, determine the rate when NO2 minus equals 0.05 and NH4 plus equals 0.6. So what I want to do is just redraw this table a little bit. We've got here he is saying he's going to redraw the table, he's not even got a pen in his hand. We've got NO2 minus, starting off just like in the table, 0.01. We've got NH4 plus, get off, NH4, it's all going pear-shaped now, isn't it? So here we are now, I'm sorted out. So you can see that what I've drawn out there is the top line, is experiment 1 there. Now the new information the question's given us is that NO2 minus is going to change to 0.05. I swear I chose a green pen for that, you know. And the NH4 plus is going to go to 0.6. 6. The question now is, how is this rate going to change? Given I know that this is first order, this with respect to NO2 minus, the rate of reaction is first order, and NH4 plus, the rate will also increase proportionally to my increase here. So let's look at the increases I've got here. 0.01 to 0.05. If I do 0.05 divided by 0.01, I will get 5. Check it if you're not sure. And so I have an increase here of times 5. So what does that mean for my rate? Well, I've said it's first order. We know it's first order because we've been down here and said that it's first order. So if this is times by 5, I will need to times this by 5 as well. So working it out, what have I got? 5.4 times 5 is going to give me, well, it's not going to give me 5. It's going to give, I'm going to times it by 5, that's right. Times 5 is going to give me, I'm going to have to put, it's going to give me, and you should try this out. Oh, here we go, his pen's not working again. 2.7 times 10 to the minus 6. So that's my rate if I've got a change of times 5 by NO2 minus. But what is also happening, so a bit of purple, what is also happening is that this rate, this concentration is increasing. 0.6 over 0.2 gives 3, so it's an increase times 3. Since I know that's first order too, I know that my rate has got to also be times by 3. But if I times this number by 3, then I'm going to have two different rates, because there's an increase in concentration here and here at the same time. So I've already worked out what the rate increase would be with just the NO2 minus increasing in concentration, and I've times it by 5. Now what I need to do is say, well, I did this bit first and my rate increased. Now let's do this bit as well. And so my increase this time, I times my new rate, which I've already worked out for the NO2 minus increase, I times that by 3. So timesing that by 3, I should get 8.1 times 10 to the minus 6. Don't trust. So what I've done here is do it in 2 steps. I've worked out the change of rate given that change in concentration. Then I've worked out that change in concentration and timesed it by the new rate from the first one. So I've done it in 2 steps. What I could also say is, well, I've got an increase of 5 there and I've got an increase of 3 there. So 5 times 3 equals 15. So here, if I've worked out that times that, my total change in rate will be 15. And if I times 5.4 times 10 to the minus 7 by 15, I will get the same answer. So there's 2 ways of doing it, if you like. The idea here then is each time you have to include both increases in concentration, and you can do that times 5 on one, times 3 on the other. So times them together, that gives you the overall change that you get for your rate. And there, your rate times by 15 gives you the answer. But you can do it in 2 steps, timesing by 5 first, timesing by 3. So to finish this question off then, what do you actually need to write in the booklet itself? If you haven't completed this question already. Determine the order of reaction. We've already said that it's first order, and the ideal thing to write here then is from the experiment 1 and 2. You're showing that NO2 minus doubles therefore the rate doubles, and therefore it's first order. And from experiment 3 and 4, we said before, ammonium doubles, rate doubles as well, so concentration of ammonium. Remember those square brackets there that you've got here? Those square brackets indicate concentrations, shorthand for saying the concentration of ammonia. Oh, sorry, ammonium. Then finally, this is the question we've got, and we don't really need to go through this now. It's just to show, there you go, there's the answer there as well, 8.1 times 10 to the minus 6. So there I've done it in 2 stages again. Question 5, same style of question again. Just remember I've got to put my experimental data in here, so we've got experiment 1, 2 and 3. Now we're looking to find the order of each reaction. Here we've got Br2 remaining constant, the concentration of Br2, but NO is doubling, so that's going by times 2. And it looks like here I've got an intrinsic, well, 4.5 divided by 1.1. I reckon that's being times by 4. Don't trust me on it, do it yourself, check it. Then we've got a little bit of a problem here because, yeah, this is the tricky part of this question, isn't it? We've worked out then that with respect to NO, what order of reaction is it? Times by 2 here, times by 4 there. It's a second order reaction, isn't it? It's being times by 2 squared here. So it's proportional to the square of the change in rate, the change in concentration, sorry. Now, we've got a bit of a dilemma here because where the concentration of bromine changes between experiment 1 and 3, or between experiment 2 and 3, we've not got a constant NO. So in this case, what we've got to do is work out, well, say I take experiments 2 and 3. Again here, I'm timesing by 2. Since I know this is second order now, NO, I know that here I'm going to times by 4 again. What is my result when I do that? My result is, in actual fact, the same answer, 1.8 times 10 to the minus 1. So that means, since I know that NO from my initial calculation is second order, as this is doubling, I must take into account what would happen to the rate. So I must times it by 4. And I actually get the same answer, which means that when bromine has doubled, there has been no effect on the rate, because all the effect on that rate is coming from this second order increase. So this is doubled, so this is quadrupled. So bromine has had no effect. The change in concentration of bromine has had no effect. Therefore, I can surmise here that bromine must be 0 order. So like in the previous example, so we can keep this, well, we can see this while we're trying to do this, the next part of the question. Further down the page it says determine the rate when NO, concentration of NO is equal to 0.05 and Br2 concentration equals 0.01. So I've drawn out the top line of the table again with the NO and the Br2 and the rate there, so it's just the same as that experiment 1 there. And then I've put the new concentration of NO in here as 0.05. I'm going to completely ignore the Br2 for a very good reason. What is the order of Br2? Yeah, 0 order, isn't it? So 0 order is not going to have any effect on the rate. So I'm only interested in this. Now here, if you do 0.05 divided by 1, you will get 0.05. So we've got a decrease in concentration here. And that decrease, if you times 1 by 0.05, then you get that decrease. So the rate must also decrease by a factor of 0.05. What have I got to remember to do to it? 0.05, remember it's second order with respect to NO, so it's 0.05 squared. So if I times the rate by 0.05 squared, I should get the answer 2.75 times 10. I can't remember, to the minus 5, I think. Okay, so there we're ignoring the bromine because it's zero order. Again, I'm just saying, okay, well, this change in rate here, we've got a decrease, but still, what do I times 1 by to get that 0.05? And it is 0.05. And so I've got to square that value and then times it by rate because it's a second order reaction. And I get the answer there. Just quickly, I'll run down the bottom here how you put that question. Determine the order with respect to NO and Br2. So I've said from experiment 1 and 2, NO doubles, rate increases by 4, therefore second order. And the next one, from experiment 2 and 3, NO doubles, rate increases by 4. So we're doing that check, aren't we? There's no increase outside of the increase from NO, so therefore Br2 has no effect on the rate and is equal to zero order. And perhaps I should write as a little correction here, rate increase therefore second order, and it's always important to write, I'm being very lazy here, sorry, with respect to NO. So that's your written communication. It's always got to be good to get in. Apologise with respect to, and say which one. So therefore second order with respect to NO. If you put that in all of your answers, you're sure to pick up any marks that would go for written communication. Final example then on this video, question 6, which is on page 20 of your notes. Again, we're trying to determine the orders of the hydrogen concentration and the NO concentration. Looks a bit more like an exam question here. It's given us the equation, but the question is essentially the same. Now, the tricky thing again here is, if you look, I'll just write in my experiments. We've got experiment 1, 2, and 3. Looking across, NO is constant in experiments 1 and 2, so we can work out easily the order with respect to hydrogen. So here we'll quickly, this one, again, don't trust me, work it out for yourself, but that looks like it's times by 2. Here, if I'm looking at 3672, that also looks like it's times by 2. So I'm fairly certain here now that with respect to hydrogen concentration, the rate will increase by 2 if you double it, so it's first order with respect to the hydrogen, this reaction, the hydrogen concentration. Now it's done that tricky thing again where it's not kept any of these hydrogens constant, so it's very difficult to work out what the NO situation is. Here we'll see, and I'm just trying to think which ones I might like to use. Let's use 2 and 3. So between 2 and 3 here, 6 over 4 equals 1.5, so this has got an increase of 1.5. Apologies for that little bit there. You've got an increase there of 1.5. Now, I've lost my cursor. Now we've got an increase of NO here. 18 divided by 6, I think, gives 3. So we've got an increase here of times 3. And we've got an increase of rates. I'm going to have to pause to find my cursor. Work out what you've got an increase of rate here between 0.072 and 0.324. What is that increase? If you do the calculation, come on, 0.324 divided by 0.072, you should get the answer 4.5. So the rate has increased by a factor of 4.5. Now, this is an interesting because you've got an increase of a factor of 1.5 there and an increase of a factor of times 3 there. If you work out 1.5 times 3, what does that give you? You may find that remarkably it gives you 4.5. Now this means that the rate has been times by 1.5 and it has also been times by 3. So what I'm suggesting here, and let's check it, let's get a different colour. What I'm suggesting here is if you times 0.072 times it by 1.5, you should get 0.108. So that's the contribution when I've increased the hydrogen concentration. I've times that by 1.5 here, I've times it by 1, so that's the contribution there. Now what you should find is, if I now times that contribution by the contribution of NO, so if I times it by 3, I should get 0.324. Check it just to make sure, but I'm fairly certain that 0.108 times by 3 equals 0.234, which is the same as doing what we've just done, timesing by 4.5, which is what we worked out just a little bit earlier on. So what we can say is that we've checked the two contributions. We've checked the contribution from here. We know that this is first order. It's increased by 1.5 times here, and we've said okay, that increase by 1.5 gives me 0.108 on my rate. Then I know to get from 0.324, or to get from 0.108 to 0.324, I can times by 3. Check it. Even do 0.324 divided by 0.108 to check, which means that the contribution of this times by 3, this increases also times by 3, and therefore we have, with respect to NO, the concentration of NO, another first order reaction. So there's really two ways of doing that. You can either check what the difference is here and then compare it to the two differences there, and we saw that it was 4.5, it was 4.5 there, so it must have been first order. Or you can do it the step method. You can say, well, what was the contribution here to the rate? There it is, that's the contribution. Then what's the difference between the actual rate and what I found out? Times by 3, first order again. So that's a really quick run through a few questions in our booklet. Let's just have a look down the table how I've answered that determination of the orders. Here we go. So from 1 and 2, H2 doubles, rate first order. Of course, I've not written in again, as I should have, with respect to H2. I'm doing it so the computer doesn't crash, but if you write that out, you're guaranteed to get your quality of written communication. Then finally, we look at the rate stepwise. We look at the contribution of the H2, and then we look at how much the NO has increased, and therefore first order again. Ooh, I've lost my recording. With respect to NO concentration. Brilliant.